The power output, also known as the luminosity or more casually the wattage of the sun, is 3.8 times 10 to the 26 watts. This is enough energy in 1 second to supply all the power that human civilization needs for 600,000 years. And gosh, that's a heck of a lot of energy in just 1 second. And so this begs the question, where does the sun's energy come from? And so that's what we're going to address in this video. Now, paradoxically, we are going to first address the question of where does the energy of the sun not come from? It can't be a big hunk of coal burning. You can do the calculations of how much energy is released from burning coal or wood or oil, whatever flammable thing you want to think of. And the chemical reactions from a sun-sized chunk of coal to produce this amount of energy, the sun would only last a few thousand years. And it can't be gravitational energy release. Now, on the next slide, I'm going to explain that a little bit more. But gravitational energy release comes from objects falling onto a planet or maybe the sun. And comets and meteoroids do, in fact, hit the sun. But and when they do, they release energy, the energy of that impact. But that is not enough to account for the energy output of the sun. It would only last for about 100 million years. Now, Hermann von Helmholtz and William Thomson, also known as Lord Kelvin, after whom the Kelvin temperature scale is named, they actually thought, 100 years ago, plus more than 100 years ago, thought that they had explained where the energy of the sun comes from, because 100 million years is a long time. And in the time of Kelvin and Helmholtz, it was thought that the Earth was, millions of years old, and but not billions of years old that we know that it is now. And so it's not that. Now let me address a little bit more what gravitational energy release is. So if you have an object, I've got this brick here. If I let go of it, it has what's called gravitational potential energy. If it falls, it will accelerate it, hit the ground. It gains kinetic energy as it falls. And, really that's the energy that it had in me lifting it up initially before I let go of it. So when things fall onto, say, a planet, a lot of energy is released. Now, in the case of big rocks falling on a planet, for instance, that would create a crater. So the craters of the moon, the craters on Earth and other planets are due to an explosion when an object hits the planet. This particular picture here is a crater. It's about a mile wide. It's in Arizona, an impact about 50,000 years ago. But this was an object that hit the Earth that was maybe the size of a room, a large room, and hitting the Earth. Yet it made this crater that was a mile across, or is a mile across. And so you get a lot of energy release from things falling, that gravitational energy. And Kelvin and Helmholtz were thinking, well, all the material that went to creating the sun had to fall in, and that would release gravitational energy. And like I said, that would account for the current energy usage of the sun for about 100 million years. Sounds pretty good. But 100 million years is not long enough, because we now know that the Earth is way older than that. So it can't be gravitational energy release. Now, gravitational energy release is important in the history of stars, because when stars do first form from a nebula, we'll talk more about this process later, but a nebula, and it gravitationally collapses, that hydrogen and helium that collects in the center to form the star is going to be very, very hot at the beginning, not because of the nuclear reactions, but because of gravitational energy release. But part of that heat then will initiate the fusion reactions that ultimately are the stable energy source for the star. And then gravitational energy release is also important for planets. Planets, when they form, like the Earth was initially entirely molten, and that's because the energy released when the things came together, smashed together, to create the planet. And that allowed the Earth, for instance, to be differentiated with most of the iron and nickel in the core, for instance. So gravitational energy release is an important concept, but is not the energy source of the sun on an ongoing basis. And so it can't be a chemical process. It can't be this gravitational energy release. The reason it can't be chemical is just the amount of energy released in chemical reactions is too small. Now, I'm using a term here, electron volts. The exact unit doesn't matter, but it's a unit for measuring energy. And the amount of energy that is involved in a typical chemical reaction of individual molecules is in the order of a couple to a couple dozen electron volts. I'm talking about per molecule or chemical reaction at the microscopic level. Whereas the amount of energy released in a nuclear reaction, which is involving the nuclei of atoms, is typically in the millions of electron volts. So you get millions of times more energy out of nuclear reactions than you do out of chemical reactions. And so this raises the question, why are nuclear reactions so powerful? And now let's review real quick nuclei. You know what a nucleus is. It's the center of an atom. You got the electrons in orbit around the center of the atom. It's the electron cloud bumping up against other atoms. That's all chemistry. But in the very center, you have nuclei. And what are nuclei made out of? Protons and neutrons. But protons have positive charge. And what do positive charges do to other positive charges? Like charges, positive and positive, they're going to repel each other. So protons with this electromagnetic charge, protons, you think, oh gosh, positive repels positive, how do they even stay together? Well, there has to be another force, and that holds nuclei together. And that other force, it's been given a name. It's called the strong nuclear force. That's the actual official name. And it's a very short range force. So the protons and neutrons have to get really basically touching before it takes over, but then it locks them together. And so the protons repel each other due to the electromagnetic force. Positive charge repels positive charge. But the strong nuclear force is so much stronger than the electromagnetic force that it holds the nucleus together. And it's the fact that the strong nuclear force is so much stronger than the electromagnetic force that explains why nuclear reactions produce so much energy. And when creating a nucleus, if you have a nucleus that has multiple protons, you have to do work, because those protons repel each other, you have to force them together before they even can get together enough for the strong nuclear force to bond them. And so then if you have a nucleus of bonded protons and you break it, you release a lot of energy, and that's called binding energy. Now I want to mention these two very similar sounding words, fission and fusion. So fission is taking a large nucleus and breaking it up into small pieces, whereas fusion is the joining together of small pieces to make a larger one. So fission is splitting, fusion is joining. Now both of these processes, when we're talking about the nuclei of atoms, can release energy. Now, Cecilia Payne was an astronomer back about 100 years ago, and she was the person who used spectroscopy to show that stars are made out of primarily hydrogen and helium. So stars are mostly hydrogen, and what's left is mostly helium with a few small percentages of other elements. So she was the one, though, that figured out that hydrogen is the bulk of what a star is made out of. And hydrogen is the simplest nucleus. And so it makes sense that, if we're talking about nuclear processes, fission or fusion, it's got to be fusion that we're talking about as the nuclear reaction that's creating the energy of the sun. Because the hydrogen nucleus is just a single proton. There's nothing to split. And so it must be protons, hydrogen nuclei joining in a fusion process to release energy. And that's the source of the energy of the sun. And so, as I mentioned before, if you're building a nucleus from scratch, you have to force the protons together against the electromagnetic repulsion. So they get close enough together that the strong nuclear force binds them together. And so it's only in the core of a star, the center of a star, where the pressure and the temperature is going to be extreme enough to force the protons together to fuse. Now, we use this process of fusion in our biggest nuclear weapons. So here's a simple diagram of a some people call them a hydrogen bomb or a thermonuclear bomb, where you have hydrogen and you actually have a fission bomb, the kind that were used at the end of World War II. And the fission bomb actually produces the temperatures and the pressures necessary to then fuse the hydrogen in the bottom part of this diagram. And so I'm trying to make this connection to other things you've heard of before. And so if you've heard of A-bombs or the atomic bomb, that's referring to a fission bomb with uranium splitting uranium. And but hydrogen bombs, which were invented later, are much, much worse. And so our biggest hydrogen bombs are equivalent, each one of those can be equivalent to hundreds of fission bombs, like the ones used at the end of World War II. So where could fusion reactions happen? I've already mentioned the core, but why? Well, if you have ever gone swimming in let's say a deep pool or the ocean, and you just free dive, you go down to the bottom of the pool, do you know how your head feels squeezed the deeper you go? There's a fancy phrase for that. It's called hydrostatic equilibrium. And it just means that as you go deeper in the swimming pool, you have more and more water overhead that is pressing down, that literally the weight of the water above you is pressing down. And so the pressure becomes greater and greater the deeper you go in the swimming pool. And so it makes sense that then the center of the sun is where the pressure is going to be the greatest. And that's where the nuclear fusion reactions are going to happen. Also, when you compress a gas, it gets very hot. And so you also need temperatures so that the protons are moving really, really fast. Remember, temperature is a measurement of how fast the protons are moving, or the particles. And so the particles are moving so fast that when they aim towards each other, they collide, and they can get close enough for the strong nuclear force to then fuse them. So that's the idea. So that's why it has to be the center. Now, so what's going on is effectively taking 4 hydrogen atoms, or 4 hydrogen nuclei, I should say, which remember is just a single proton, and fusing it to make a single atom of helium. So helium is number 2 on the periodic table, and most atoms of helium are helium-4. That is, they have 2 protons and 2 neutrons. And so this is what this was figured out by Hans Bethe in the 1930s. It's called the proton-proton chain. And the net result of this chain is you have 4 hydrogens make a helium. But it's not directly, literally 4 protons coming together at one spot and immediately forming a helium, because that's very unlikely. What's much more likely, as all these particles are jiggling around, is that 2 protons are going to collide with each other. And so that's step 1 in the process. The 2 protons collide with each other and they fuse. And one of the protons turns into a neutron. And that's a process called beta decay. I don't want to get too much into the detail. It does eject another subatomic particle called a neutrino and another subatomic particle called a positron. You can think of a positron as basically an electron but with a positive charge. And so those fly off, and you now have this deuterium nucleus, that is a hydrogen nucleus with an extra neutron, proton and neutron bonded. And then that hits a proton, because remember, most of the particles around are protons. So that hits a proton, and then that becomes helium-3. 2 protons with 1 neutron becomes helium-3. And then in this mix of gas, if 2 helium-3s collide, they will form a helium-4, and 2 extra protons will pop off. And so that's step 1, step 2, and step 3 of what's called the proton-proton chain. The net result, like I said before, is as if you had 4 protons, this one, and this one, to make this, plus then the other one. And so you've got 4 protons coming together, effectively, to make a helium nucleus. And that's where the energy of the sun comes from. Now this graph, remember I used this phrase binding energy, how much energy is stored in this nucleus, or in any nucleus. Well, it turns out that the most bound together nucleus is iron. It is the most stable isotope or nucleus. And so, and that's because iron has the most binding energy per mass, or per nucleon, which just means a proton or neutron. And so the iron nucleus is the most stable. And so any nuclear reaction that goes towards iron in this chart, so this is binding energy as a function of the mass of the nucleus. Any nuclear reaction that goes towards iron will release energy. So you take a big nucleus and you split it. For instance, uranium in a fission bomb or A bomb will release energy. Or if you take hydrogen and fuse it to larger nuclei, it will also release energy. Any movement in that direction. And so going back to the A bombs versus hydrogen bombs or thermonuclear bombs, this is just meant to illustrate again this is really just difference between fission and fusion. That a fission bomb, think of a like the mushroom cloud end of World War II. Whereas these thermonuclear bombs on this scale, this is like a bar chart, are just much, much bigger because fusion produces much, much more energy than fission does. And both of them produce way, way, way much more energy than chemical reactions do. Now, there's another way to think about all this that's maybe a little less confusing than binding energy. I strongly suspect you have seen this equation before, E equals mc squared. So this is Albert Einstein's famous equation that came out of special relativity in 1905, and this equation in 1906. And basically what this equation is saying is that energy and mass are 2 aspects of the same thing. Or put another way, you can convert energy into mass. Now this c here is the speed of light. So you know the speed of light, 3 times 10 to the 8 meters per second. That's a big number. That's a big number. And then you square it, it becomes a huge, huge number. And if you multiply that by the mass, you're multiplying a mass by a huge, huge number, you get a lot of energy. So a little bit of mass converted into energy is a lot of energy. And it's this equation that explains how nuclear weapons are such terrible things, because it's converting a little bit of mass into a lot of energy. And you release a lot of energy in one space of one time, That's what an explosion is. Now, getting back to stars, the mass of a hydrogen atom is 1.00794 Daltons or atomic mass units. We don't need to worry about it, but it's 1.00794 something, okay? 4 hydrogens together, if you take 4 times this, that's what you get, 4.03176. But the mass of helium-4 is 4.002602. That is less than this by a little bit, and the difference is 0.029 atomic mass units. And that is 0.7% of this. So when you take hydrogen and you fuse it to make helium, you can think of it as 0.7% of the mass disappears. 0.7% of the mass gets converted into energy. And that's where the energy of the sun is ultimately coming from. And so it's 0.7% for this nuclear fusion reaction. Doesn't sound like a lot. Technically, this also applies to chemical reactions. But chemical reactions, the differences are more on the order of 0.000001%. Way less than nuclear reactions. And so in the center of the sun is where we have really super high temperatures, high pressures. That's where the fusion can take place to release the energy. I've mentioned this diagram before. Just want to point out the density is around 200 grams per cubic centimeter in the very center. The temperature is about 16 million Kelvin in the very center of the sun. And so those conditions are sufficient to allow these fusion reactions to go on. This is also why when we think about nuclear power here on the Earth, we have nuclear power plants, but they all use fission. They all use fission, uranium, produce lots of radioactive waste. Engineers and scientists around the world are trying to make a nuclear reactor that will work by fusion. But the problem with that is, how do you contain a reaction that's going to be 10 million degrees? What do you put it in? And that's the problem. And but in the sun, you've got gravity holding everything together at 16 million degrees there at the center. Now, feel free to pause this video here to look at this slide. And this is really just summarizing the upshot of everything we talked about. Please do not feel like you have to memorize the individual steps of the proton-proton cycle. I don't need you to do that. But what I do want you to know is effectively you're taking 4 protons, 4 hydrogens, and making 1 helium. And this proton-proton chain is the dominant energy source in small stars and medium-sized stars like the sun. Just as a last thing, I want to mention the most massive stars, the biggest stars, much bigger than the sun, actually use a different nuclear reaction here called the CNO cycle. And in the CNO cycle, carbon, nitrogen, and oxygen get used as catalysts. Now, in what a catalyst is, it's something that's involved in a chemical reaction, but it doesn't get used up in the chemical reaction. It's an assistant, so to speak. And so in the CNO cycle, see, there's a hydrogen comes in here, hydrogen that comes in here, hydrogen comes in here, hydrogen that comes in here, and 1 helium-4 comes out. And so this is the cycle. And feel free to pause the video and actually study it. Here's the key. The reds are the protons, neutrons are the grays. I mentioned neutrinos. That's this little symbol. There's a neutrino flying off here. I had mentioned positrons earlier, like a positive electron, small particle, but with a positive charge. So that's this. And so you have this cycle. And I'm just mentioning it in passing here. This isn't so much relevant for the sun, but is for more massive stars. And here's additional captions here for this. And I'm going to stop here. That is a quick introduction to where the energy of the sun and other stars comes from. And we will continue on with other topics about the sun in other videos.